Welcome back. So let's look at our second Thevenin and Norton problem. So this problem here is asking us to find the Norton equivalent circuit. So we're going to need I Norton and R Thevenin. Zoom in just a little bit there. All right. So looking at this problem, let's see what we got. We have a current source and then we have a voltage source. So two different types here. But running through our steps, so do we see any dependent sources? And I don't see any. So we are good. So let us go and zero out our sources. So we'll take any batteries that we have. We'll turn those into just wires. Then any current sources we have, we'll turn those into clipped out sections. We'll just clip them out of the circuit. So let's go and draw that. So drop our 15 right there. Drop our 25 right there. Replace our battery with this wire. And we'll replace our current source with this clipped out bit. And let's go ahead and drop plus minus and then VOC over here. They don't always include it. So plus minus VOC. All right. So now we'll work that way to find our equivalent. So if I was to take this resistor and slide it down to right here, I'll see that these two are in parallel. So I'll go write R parallel 1 is equal to 15 times 25 over 15 plus 25. And that will give us zoom in just a little bit. That will give us 9.375 ohms. So if we go and redraw that, where we have that R parallel 1, where it's 9.375. We have plus and minus VOC. Yep. We'll notice that R equivalent is equal to R parallel 1, so only resistor, and that'll be equal to R Thevenin. So R Thevenin is 9.375 ohms. Okay. So now that is that's one part. So we have R Thevenin. But now we need to jump back to the original circuit and use previous methods to solve for these other values that we need. So I'm going to scoot up just a bit. Okay. So let's go ahead and redraw this circuit. Plus minus 10 volts. Here, this will be 25 ohms. Start 15. And that's 1 amp. Let's not forget we have the plus minus VOC over here. Okay, so original circuit. Now this is a little bit more complicated than our previous examples because now I've got current being pumped up through here, and I've got current being pumped up through here, and I need to find VOC. Well, this entire thing isn't quite simplified yet. But we know that branches in parallel have the same voltage, right? So this open terminal voltage will be the same voltage as here and there, as here and there. And we know that voltage along this wire is going to be the same. So there, so that has the same voltage as right there, which has the same voltage as right there. And we know that this voltage will have the same voltage as right there, will have the same voltage as right there. So if we can find this voltage drop across this resistor, we can find the open terminal voltage. And since we have two separate sources, this is kind of pointing us in the direction of doing a nodal analysis. So I'll just go and write that out. So, but to do that, we'll need to drop a ground. V of ground is equal to 0. And then let's name this point V of A, just for convention wise, we'll name it V of A. You have to do this during the test for nodal analysis, just name your points. You can name them whatever you want. Okay. So V of A, what we're going to do is assume that all of our currents, this node, are leaving, except for known current directions. So right here, this is coming up, it's 1 amp, and it's going to have to go and pass into V of A. It can't go down this open terminal, so it has to go that way, so it's entering. So if we write, I'll call that like I1, call that like I2. Okay, so I1 plus I2 minus that 1 amp that's entering, that's equal to 0. And this is just the nodal analysis with the KCL. Okay. So something that we need to know is right here at this point, that is going to be 10 volts from this battery because we're down here at 0. We're going to travel up through this battery, pick up 10 volts, and end right there with 10 volts. And then we're going to cross over this resistor, and we're going to lose a little bit. So now what we'll do is go and fill all of this out. So I1 will be V of A minus 10 over 15 plus V of A, so this is I2 right here, so V of A going down, minus 0, we're ending at 0, over 25, minus, bring that 1 down, is equal to 0. Alright, so let's go ahead and split all this up. So we'll have negative 10 over 15 plus 1/15 V of A plus 1/25 V of A minus 1 is equal to 0. Okay, so now what I'm going to do is come up here and I'm going to combine my knowns, my known constants, and then I'll combine my unknowns. So here, V of A will be 1 over 15 plus 1 over 25. We're just factoring out the V of A. This will be 1 plus 10 over 15, which would be 15 over 15 plus 10 over 15, which will give us 25 over 15. Okay. So then now if we were to solve for V of A, that would give us Okay. Looks like this would give us 15.723 volts per V of A value. You might be wondering, what the heck? Why is that point? Why does this point pick up voltage from there? This had 10. How could this have 15.7? Well, you're gonna have some coming up from here. It's gonna provide a little bit, so that's a-okay. Okay. So now that we know what V of A is, let's go ahead and find out what that would be. So this is the 25 ohm resistor. This is V of A. So 15.723 volts. And this is V of ground down here, which is 0 volts. So let's find the voltage drop across there, which would just be, any guesses? 15.723 volts. So that is your V Thevenin. Okay, so now we have V Thevenin. All right, but it's not asking us for the Thevenin voltage; it's asking for the Norton current. So let's go ahead and use our relation that we had. We know that I Norton is going to be equal to V Thevenin over R Thevenin. So we can write 15.723 volts over 9.375 ohms. I Norton is going to be equal to 1.67 amps. Okay. So that is all three of our values. So if we were to go and drop that in our Norton circuit, plus minus VOC, we would just have this. Okay, so this is our Norton equivalent circuit. Okay. And then in the next video, I'm actually going to rework this problem, but using a different method. So make sure to check out that video right after this one.